Sometimes, even if you're careful, or you have, unfortunately, a large system, and if you, for example, come further down in the periodic table, the question is, where is the valence? I mean, is it just the outer, I mean, chlorine, is it just really 3s and 3p? What about those 2p orbitals? Or transition metal complexes? There it's in, what about the d orbitals? Is it only the 4s and 4p, but what about the 3d? So you might be forced to use an active space which gets too large. And in the program we are going to use this afternoon, which is the Dalton program, because that's the one I know best about, at least the MCF part I know best. You can do also MCF calculation, Gaussian tried, and I don't think I ever want to. But we do it with the Dalton program, and there's another method implemented, which is sort of a generalization of this complete active space, which is called restricted active space. RASSCF. And in the first place, this sounds sort of also again a contradiction. I say it's a generalization of the complete active space, and then the thing is called restricted. The idea is what you do, if I have sort of a set of here unoccupied orbitals, let's have some more, and have a lot of occupied orbitals, and I would like to do a complete active space calculation in this active space. But this active space is just too large. I get too many determinants configurations. What do? I can split it up. In 3 parts, which are then called RAS1, RAS2, RAS3. That RAS2 space, that's what used to be the complete active space. And there you do precisely the same. You make all, let's say these were all occupied. Here in that RAS2, you still do a full CI in that with those orbitals. So you make all determinants which you can get by distributing those electrons, in my case here 4, over those, 5 orbitals. So that's still full CI in here. But we would also like to include some subvalence orbitals or electrons. And I can see there, for example, or I can see there are some other unoccupied orbitals which would be important to include, or actually both. So what you do, what the program then does, it generates some extra determinants or configurations. By the way, that you allow some excitations out of RAS1 into RAS2, and or, depending on what you ask for, from RAS2 to RAS3. And there you can, in the program then, or in the input, you can tell it what kind of excitations you allow. So how many electrons you're allowed to move from this RAS1 into RAS2 in order to generate extra configuration determinants. And what you actually specify, at least in the Dalton program, is not how many electrons you're allowed to move, but how many holes you're allowed to make. I mean, how many you're allowed to take out. And that could be 1, 2, 3, 4. I mean, whatever you can you believe you need and can afford. So here you tell how many electrons are allowed to remove, so how many holes, and correspondingly up there, you tell for this RAS3, you tell which orbitals you want to include and how many electrons you want to allow in there. And then the program will generate extra determinants where it has to put, when you say from, for example, from 0 to 2, then it will make extra determinants which correspond that you have excited from this space to that space single and double excitations. So you extend your set of determinants with specific ones. Single and double. I mean, typically you do single and double. Sometimes maybe. I did sometimes triples, but so this is sort of a compromise. You can't do all of them. All would be as many electrons as you would have. I mean, if that RAS3 is like this, where I have 4 electrons in, if I would say from 0 to 4, then I just can include it to the RAS2, because that's all again. But I could say from 0 to 2 electrons you're allowed to include in there. And then up there also single doubles.